Hello everyone, welcome back. In the previous videos, we have already learned how LDR, STR, LDRB and STRB work in ARM mode. So, do we need to learn them all over again for Thumb-1? Not really. The functionality remains exactly the same. LDR still loads data from memory. STR still stores data into memory. Byte, half-word and word accesses behave exactly as before. So what's different? The difference lies in the 16-bit Thumb-1 instruction encoding. Because Thumb-1 instructions occupy only 16 bits instead of ARM's 32 bits, they have fewer bits available to encode registers, offsets, and addressing modes. As a result, Thumb-1 supports fewer addressing modes and introduces several instruction restrictions. In this video, we will focus only on those differences. Addressing modes supported in Thumb-1. Register Indirect. Let us consider this example LDR R0, content of R1. This is the simplest addressing mode. The processor treats the value stored in R1 as a memory address. It accesses the memory location, reads the 32-bit word stored there and copies it into R0. In other words, the address comes entirely from the base register without adding any offset. Next, we have immediate offset. For example, LDR R0, content of R1, #4. In this addressing mode, Thumb-1 first adds the immediate offset to the base register. Here, the effective address becomes R1 plus 4. The processor then reads the data stored at that new address and loads it into R0. One important point is that Thumb-1 encodes immediate offsets differently depending on the instruction. For word transfers, the offset is encoded in multiples of 4 bytes. For half-word transfers, it is encoded in multiples of 2 bytes. For byte transfers, the immediate value is used directly. This is why some offsets assemble successfully while others do not. Next, we have register offset. Example for that is LDR R0, content of R1, R2. Instead of using a constant offset, Thumb-1 uses another register as the offset. During execution, the processor adds the contents of R1 and R2 to form the effective memory address. It then reads the data stored at the address and loads it into R0. PC relative addressing. LDR R0, content of PC, #16. Here, the program counter acts as the base register. During execution, the processor adds the immediate offset to the current PC value to form the effective address. It then reads a 32-bit constant stored in the literal pool and loads that value into R0. Then we have SP relative addressing. For example, LDR R0, content of SP, #8. In this addressing mode, the stack pointer acts as the base register. For the LDR instruction, the processor accesses the memory location at SP plus 8, reads the data stored there and copies it into R0. Now let us understand ARM addressing modes which are not available in Thumb-1. The very first addressing mode which is not available in Thumb-1 is pre-indexed with write back. For example, in ARM mode, we can write something like LDR R0, content of R1, #4 followed by a factorial sign. ARM can automatically update the base register after the memory access. Thumb-1 cannot do it. Next, we have post index. For example, LDR R0, content of R1, #4. ARM can first access memory and then update the base register. Thumb-1 does not support post-indexed addressing. Next, we have scaled register offset. For example, LDR R0, content of R1, R2, LSL #2. ARM even allows the register offset to be shifted before the memory access. Thumb-1 completely removes this addressing mode. Let us understand one more Thumb-1 restriction. LDR R0, content of R1 is valid, but LDR R8, content of R1 is invalid. This is another important Thumb-1 limitation which involves register usage. General Thumb-1 load and store instructions operate only on the low registers, which are R0 through R7. High registers, that is R8 through R15, cannot be used with these general Thumb-1 load store instruction encodings. Thumb-1 also uses smaller immediate fields than ARM, which further limits the range of offsets that can be encoded. That's all about this video. I'll see you in the next one.